So now I'm going to start out. Benson and I are the chairs for this initial keynote session, and we're thrilled to start out with the introduction of Xin-Woo from AMD. He's going to be talking with us on integrated circuits, heterogeneous integration, and interdisciplinary engineering, which is a wonderful discussion for all of the different disciplines that we're covering here. Xin-Woo is the Vice President of Silicon Technologies at AMD. He started out with Xilinx in 1993, and he's gone through many different technology progressions, starting with 0.6 microns and moving up to 3 nanometers. So that's been a lot of technology along the way. And currently, his responsibilities include silicon technology, heterogeneous integration, advanced packaging, and thermal mechanical solutions, all of the types of things that we were talking about today. So join me in welcoming Xin-Woo. And again, thank you very much for making the trip to be here.
Thank you. Thank you, Nancy. Thank you for Binghamton University. My name is Xin. I'm with AMD. It is my honor and pleasure be here, be able to talk to all of you. Today, I prepare a few pages. Mostly, it's really not for industrial talk, or it's more through our own experience. We have been doing a lot of hetero-integration today. We call it the 3D IC, and just want to share with you. I'm with Xilinx before. Xilinx was my first job and only job until recently. Now we're part of AMD. As a bigger company that we, AMD offers all kind of high-end, high-volume semiconductor chips from like CPU, GPUs, FPGAs, semi-customer solutions, even ASICs. So pretty much, if you want to say what the main stream of AMD offer is, pretty much offer everything. So it is a very exciting experience for us to be a bigger part of a company and a bigger part of the industry. This is once again as a small community talk. So I start with semiconductor. When you know, this is the it's a 1956 Nobel Prize, because such a important prize, we as a community be able to sit here today to have this meeting. And then, you know, this is the, everyone knows history, that 8 of the junior young engineer left the Shockley lab to form a new semiconductor company. They signed, 10 of them signed a $10 bill, and that signified that the dollar bill served as a contract with each other. So that was a kind of a feel slightly different in the West Coast culture that is today still, as the like you see a lot of small company, bigger company have a quite different culture here. This is so-called 1965 Moore's law. You know, Dr. Moore initially say the semiconductor, the number of transistors will double for every 12 months, and then later correct to 18 months. 10 years later, it's correct to 24 months. So basically, the 2-year cadence has been the industry for almost 50 years till recently. But on the other hand, we all know we are all engineers, we're all scientists. There isn't no such a law in the natural law or even physics law say something can double by itself for every 2 years. You know, that's almost same as the one who plays chess with king say put one piece of rice in the first box, then double it for every box, you quickly realize the whole world cannot be put into the plate, right? So this is the same situation. So Moore's law really is a economical or financial optimism at the time that Dr. Moore put up there to counter the people feel, why do we want to do a transistor? The vacuum tube is a lot more reliable. It's not higher performance. Why we do that? And Dr. Moore basically say, don't worry, there will be a day we'll surpass you, all of you. So that was the spirit of the Moore's law. Right? And the law itself has been there to really two sides. One side, it indeed guide the industry. The second part is inspire the industry move toward such a 2-year cadence. All the material supplier, the equipment supplier, the fabs, the customer like we are, all toward that. For every 2 years, we gear toward the next node. We gear toward a 50% scaling. So you will double your capability for every 2 years with almost no additional cost. So if you want to say what is the key part of Moore's law, that is the part. It's not really fueling the scaling. It's not really the growth. It's really you got there with almost no additional cost. That's how makes the semiconductor today. Everyone had a phone in your pocket. If you compare with what the ENIAC, the first computer in the 1947 built in Carnegie Mellon University, this is probably a million times more stronger in your pocket. And that's actually not only that, even from the Deep Blue, the first computing.
I'm sorry, you have to really be right on top of it.
Okay. So battery run off. Okay. So even compare with the Deep Blue, the supercomputer which win the over the chess master, your iPhone is multiple thousand times stronger than faster, more powerful than the Deep Blue. So you see how the semiconductor really grows. We as Xilinx and now also AMD, I put this page just see how we did. From 1998, the biggest FPGA by then had about 27,000 logic cells. Each logic cell roughly equal to about 100 logic gates. So you can do that was the biggest FPGA by then at the quarter micron node. And today, at a production node 7 or 6 nanometer, the biggest have a 18,500,000. So basically it's 18 million logic cell. So the growth you can see it's not really 1000x, but nearly such a number. And that it's translate to roughly about 20-some years of growth. So if you take the first few years, it's almost two year per cadence, then it's a slowdown. And also the dark bar, it's really what you can do for a monolithic integration, almost represented to radical size, photolithography radical size, about 750 to 800 millimeter square. Then the orange bar is by then we call 3D IC, today we call it Hetero-Integration, and that initially doubles the size, and then quickly you can see it's a three times or now 4 times bigger than if you can do a monolithic integration. So that is really thanks to the Moore's law, to the Hetero-Integration, to packaging, and to many new technology there made us there. So what does today look like? In today, the silicon node scaling is continued. Every 2 years, TSMC come up with new technology. Today is the 3 nanometer, and 2 nanometer will be 2 years down the road. However, the scaling is really slowing down. If you look at it, the standard cell-based design, it's roughly or almost still be able to keep the pace, roughly about 40% shrink or 60% scaling. However, the physical scaling, SRAM, customized design, you are roughly getting about half. So every 2 nodes, you get about 40 to 50% scaling, but not 1 node in terms of node naming. Economic benefit, it's really almost no more. It's reduced significantly. The cost of manufacture increase, everyone knows, and everyone really concerned. One set of mask in the 28 nanometer start with $1 million. This become $10 million, roughly $10 million at the 7 nanometer, and probably 20 million at the 3 nanometer. So with a new startup semiconductor, you can calculate how many masks you can afford, make mistake for the tape out, right? So that is the economic scale. The Hetero-Integration indeed provide a chance. Initially, people have a different naming. For a period of time, it's called 3D. And then people invented a name called 2.5D, which I'm kind of against it for all the time, but I still use it myself. You know, as a math student, you know, you can achieve 2D, you can achieve 3D. 2.5D is a lot harder to achieve for half dimension. Unless you're mathematically in a Hilbert space, you can do that, but not in the real time. Nevertheless, Hetero-Integration is not a next Moore's law. It doesn't apply to everyone. It offers a variety of technology. It only suit for certain application, for certain situation, for certain technology. Not everyone to suit for it. The Hetero-Integration come in the cost. It's not free. It's not Moore's law, say every 2 years you get it free of charge. It comes with associated cost. Sometimes it's not cheap at all. So it's only suitable for certain volume of application. And the Hetero-Integration require a lot of interdiscipline engineering or knowledge. It's not a one single technology. You can name it. So next, I like to give a few examples of ourselves. So in 2011, we, by then as Xilinx, as among the first few who started a Hetero-Integration advanced packaging for FPGA. By then, we put 4 slices of FPGA into one passive silicon interposer, and that make it through the microbump, through silicon via TSV, we call it, into a package to form a new FPGA. By doing that, the purpose really, but is to save the cost. But that the first V2000 is about the radical size, even slightly less than radical size. But if you want to make a monolithic chip that size, at the 28 nanometer, I estimate with good yield, you get 2 die per wafer. If I cut into 4 slices, so each slice is a quarter of size, for the same defect density, I can yield about 100 die, 100 good die. So if I integrate 4 into 1, I get 25 good FPGA. Even I lost 50% yield, I still have a 12. 12 versus 2, you know, so that's a simple math why we did that. But it's never really a technology itself. I listed many things. Number one is product planning. What do you want to do? And then, of course, it's architect. Can your architect allow you to partition your die? In FPGA, it happened to be doable. And also, we've been thinking this for a while. In some talk I mentioned, we actually started this idea in the 0.18 technology. Of course, it's not flying. By then, the C4 is not even mature, not talk about microbomb, not TSV. But the architect is there. The architect you can see today, if you open, this is 16 nanometer technology. If you open a FPGA for the mono die, the light blue is the programmable logic part. The green is all kind of 30s from 10 gig to 30 gig. The yellow, brown, it's all kind of IOs from the legacy, even 3.3 volt IO to high performance DDR in the light blue, DDR3, 4, 5. And the dark blue is the one have the embedded processor. It's ARM processor there. However, you can see I can stack 3 of them into a bigger one, or I can stack some of them with other hard IP to become a more hetero-integrated FPGAs. So that was the idea. However, this itself, if you see what it involved a lot of design, the defect tolerance, the reliability, the EDA tools. How do you simulate the chip more than 10 years ago, multi-chip into one design? Even if you're, they may not run the same voltage, and the VCC had a different naming. By then, if you run the EDA tool, it doesn't work. It didn't recognize if you want to run the same VCC and a different name, right? So not mentioning through the boundary. So a lot of work ourselves, work with the EDA company. Later I'll show you in 3D as same situation. You have to hack it to make that work. Even logistic is quite a bit of effort and innovation, because now you can say, yeah, you put 4 of them together, but 4 of them may not have same behavior. If you want to put them, you have to say which one can match which one or not match other one. So you only have to say these die ABC have to be together, but not with the D. D have to go to the other die. So how do you handle the logistic in an automated way that you produce millions of chips without using any human or even engineer intervention there? So there's a lot of material research, packaging related at the time. This is a simple intermetallic compound formation. This was not a problem at the C4 if you are in the 100 micron dimension. It was a problem even at the time when the microbomb become a 25 micron dimension. By then, it's 45 micron pitch, so the physical bomb is 25 micron. You can see some bomb form well, some not well. A lot of work involved, especially one of my colleague, Suresh Ramalingam, Dr. Suresh Ramalingam, he's a corporate fellow AMD now. He came out, the methodology today, it's still being used in the industry. Also, I keep joking myself, we have a senior director in reliability, Dr. S.Y. Tai. He's retired now. I say half of my time work for him because all kind of reliability problem we deal with. This particular case, you can see in the die gap, it's a small gap, approximately 40, 50 micron. Initially, there will be a warpage. So the initial thinking is there is a cut in the middle. Then during the manufacture, it will keep flat. Then at the later, when you fill the molding compound fill into it. When you polish, the molding compound disappear on the top. You still have a bare silicon, but molding compound in the middle. And the other dark black is the underfill. So it's both are organic material. That should be fine, but no, it's not fine. At the temperature cycle, this is actually more than JDAC number. After 2000 cycle, you start seeing a minor crack at the bottom in some case, but not other case. And so we spend big effort try to evaluate whether that caused a real customer reliability problem or not. Here, I really want to special thank Professor Park. He was part of that. And this deep discussion or debate, go all the way to the CEO level multiple times. Eventually, we decided it should be okay for application it goes to, and indeed true after now 12 years, we have not seen any customer problem, application problem of these, but nevertheless, later this been changed. It's only less than a year material have that. So now it's history, so it's okay to talk. We did initially, there wasn't a protocol between chip-to-chip connection, so we made our own. There's about 50,000 connection between the 4 chips. So means 100,000 pair of the microbomb. If you want to talk the yield, I always say the biggest cost for hetero-integration is the yield, because you are putting many good die into one of them bad, sorry, throw other away, you can't rework on them. So initially we do worry whether we have a good enough fit rate for 1 out of 100,000 microbomb without problem. So we build a redundancy on the circuit in the connection. You can see there is one spare connection out of 256 pair. It's actually on the boundary, so you can share with both sides. So it's 2 out of 500 pair of connection. And once one gets bad, automatically you can switch to other. So now your error or your defect requirement reduced from 1 out of 100,000 become 1 out of 250, right? So that is make the idea. This has been published in the VSI 2014, but fortunately, it's never been used. So microbomb yield is excellent, way more than that. So the redundancy never been used, but it had been there to serve the purpose by the time. So that was some historical story we had, or experience we had on the first hetero-integration. Now there's many. So next one, let me talk a little bit more futuristic. This is in the industry, the whole industry really now beyond so-called 2.5D into the real 3D vertical stacking. So that is the idea. When you put the 2 chip together vertically, you reduce your connection distance to order magnitude. Take this one example. If each green cube is a logic element that say 100 by 100 micron size. So if you have a data in the one of in the middle, want to connect, move to the next one, it will take about 100 micron distance, right? And but if there's a same green cube under you or upper on you, and the thickness of each stack, roughly about 10 micron, maybe 15 micron, then you only need to travel 10 micron distance instead of 100 micron distance. So your traveling distance is about order magnitude less, and that gain your speed, gain your performance, and reduce energy consumption, and reduce your latency. So that is whole idea why people want to do the vertical stacking. So that here, someone put an equation, say Z is larger than X plus Y, right? So your vertical connectivity is far better than your X, Y altogether. So that was the idea, why you want to do that. But once again, it's really never a technology itself. Although the technology itself is quite challenged today. Later, we have an excellent talk from our colleague, Himesh, there, where he will talk first AMD product with a memory on logic. But it is really a product planning architect work to start with. If you do on wafer stacking, the fundamental challenge is there's no known good die. you don't have a choice. You stack one die on another, whether it be good or bad. How do you want to handle that situation? Or if you want to put a chip-on wafer that have a known good die, but also challenge if you want to, how do you do multi-stacking? And also the connectivity chip-on wafer would not be as dense as wafer-on-wafer. Keep-out zones. Now, even the micro connection, we call it hybrid fusion bonding. That is the copper dielectric bonding. It's about 1 to 2 micron pitch. Even that, compared with the 3 nanometer technology, you have a transistor of 3 nanometer. It's a huge dimension. So what is the stress cost or really the manufacturer cause the transistor behavior different when you're near one of the connection we call the keep-out zones. The 3D design, once again, that's even more challenge. Now you really need to design a chip which have a manufacture at each layer, then you put them together. How do you design a chip with a vertical connection? And there's other issues, RF, thermal definitely it's always been the ultimate challenge because every energy by end become heat, right? That's by the second thermodynamic law. So how do you handle them? It has to be just more than the thermal solution. We'll have our senior fellow Gamal give you an action talk later. And there will be a software issue. There will be a stacking with other hetero-integration issue. There will be packaging. There are many other issues. So this is one of the test chip we run. We see the keep-out zone roughly about a micron. When you put a million of or billion of them together, you see the data. Roughly in the within 1 micron, you see the transistor changes roughly about 1 sigma against the SPICE model. And that's really, initially people say stress. Personally, I don't believe really a stress because now we're talking about FinFET. When the FinFET is a fully depleted channel, when you put the stress on transistor, you want to make transistor change, the stress will talk gigapascal levels. All these mechanical stress is in the tens or maybe 100 megapascal, but never really reach the gigapascal level. How can that change the transistor? It really turns out to be a manufacturer once you have such a TSV there, the litho get disturbed. The transistor no longer as identical as you make a uniform 3 nanometer transistor. There will be an empty space. The polygon shape, the physical shape, is not exactly same. The slightly change that really caused the change. But it's about a micron, so it's not that big, and you can always find engineer way to handle it by putting the transistor. There's always a way to handle the problem once you know the problem. Right? Normally, we say there are 3 steps of the solution. The first step you solve in the technology itself, mostly for module, that's the best. If you don't, you put in the integration solution, that's a little bit of patch. Then you can model it. If you cannot solve it by technology, I just model them 1 sigma less. Even if that's still not doable, then we say we do a DFF, basically don't do it. Don't put transistor there, you put something there. So you can see the step-by-step, engineer always find a way to solve the problem. The next one is it's a CAD issue. It's an EDA tool. How do you want to really connect a 3D design? Today is still a hack design. Means it's not, today if you want to route a, say, standard cell library across vertical tier, it's not possible. Especially if they are not on same technology. That's not possible. So the design is still pretty much 2D, but then you add a third dimensional 1 component only, a connector. So basically it's still 2D design plus a vertical connector. That is what today we're doing. So it's not really a full 3D design, but it works as of today's capability. I mean, ideally, and I believe it down the road, it will become possible. This is a good one slide show for Dr. Gamal will give you a much detailed discussion. And this is thermal engineering. And by end, we as a chip provider, most time you don't know how people use the chip. Sometimes we know, like CPU, GPU. Sometimes we don't know FPGAs. We have 1,000 customers, how they use them. So you will have to provide them a very good thermal model. Say, if you use it this way, here is your temperature distribution. If you use it this way, here is the temperature distribution. So if you have say, I have a 4 stack of a chip. So if you run individually, you will see roughly about 30-some degree temperature raise at a certain heat solution, heat flow with a certain power. However, when you put them together on the right side, you will see the temperature raise is quite different in some chip at a different position, and also in the different XY depending on whether that particular part is hot or not, I mean run higher power or not, are they buried under or not, or if so, ideally you want to put the highest power chip on the top because that's close to your thermal heat solutions. But even that, other chips still being heated up one way or another. So by end, because of these, really the numerical simulation gave you arbitrary solution, arbitrary situation solution. However, we all know simulation only gave you as good as it calibrated. So we actually built several thermal test chips. So each, the top one is a 2-dimensional monolithic thermal test chip for it have a 4 quadrants, so you can cut into a 4 small chip or put into one big chip. And then each about 50 by 50 micron area have its own heating and sensing. So it can program into any arbitrary heat thermal map you want it to be, and then you can sense every 50 micron dimension, whether what temperature and also time dependent take how many nanosecond or microsecond to heat up. And then we put a next one is a 3-dimensional 5-layer of such a things. So 5-layer heating and 5-layer sensing to calibrate the thermal models. So by end, we Xilinx supply many different solutions for different applications. As a summary, I won't say silicon scaling is continue but being slowed down. The costs continue to increase from node to node. Hetero-integration provide new opportunities, but hetero-integration is not another Moore's law. Hetero-integration suits different application differently. It comes with a cost. The IC industry will continue to grow, especially for those heavy data processing area. You named AI, you named machine learning, you like data center, the autonomous drive, 5G, so on and so forth. Whenever you deal with the data, there's growth. Those companies or suppliers who can supply the solution to suit each case and can supply them with a lower cost will grow better. So that is the game. Basically, who had a best variety of IP and they can fast deploy them, whether through the monolithic or chiplet, and they can deploy them at a lower cost, will be the one fare better. So that's what we see. And the future success, it really requires more interdisciplinary knowledge and engineering. We're very happy, and we're actually advocated and very happy for the new government CHIP Act. Inside that, quite a bit funding, not go to industry, but go to universities. That is where the future lies. Because if we go to other countries, we see if you talk people like our age, I'm kind of old, and we feel we're pretty not bad, we're better knowledge, more experience. You talk people 20 years younger, about par. You talk people 30 years younger, there's a million of them there. We have none. So in 20 years, 20 million of them like us, and we will need ours, students, right? So that is key part. We're really happy to see the university get funding on that. Okay, so that is my talk by end. Just a normal statement. If you hear my talk, you buy stock, it's your problem. Okay, thank you.